Greetings, Internet. My name is Gabriel Wolf, and today I'd like to show you this little vacuum pump I made, and how you can make one yourself. Now, you may have looked at the title of the video and wondered to yourself, what's a Sprengel pump? And more importantly, how do I pronounce it? I've heard it pronounced both Sprengel and Sprengel. I'm just going to pronounce it Sprengel for the rest of this video. As for what is a Sprengel pump, this is a Sprengel pump. It was invented back in 1865 by German-British chemist Hermann Sprengel and was used to make the first incandescent light bulbs and vacuum tubes for studying electrons, until around the 1900s when mechanical pumps began to replace them. I want to make similar vacuum tubes for some projects I have coming down the pipe, but I need vacuum levels on the order of 0.1 pascals to keep the electrons from bumping into residual air molecules. The only pump I was able to find online that gets close was this one from McMaster-Carr, rated for about 2 pascals. However, it's pretty expensive and a bit more noisy than I would like to subject my neighbors to. Plus, the instructions tell you to replace the oil every single time you use it, which is just ridiculous. So I started looking into alternatives, and that's when I discovered the Sprengel pump. It works by using droplets of liquid mercury to catch air particles and push them out of a narrow tube. Cody's lab did a good instructional video for how to build one out of glass, which I'll link here. However, I didn't think my landlord would want me splashing mercury around my apartment, and I didn't want to risk inhaling any mercury vapors anyway. So at first, I tried to replicate it using gallium, building the whole apparatus in a foam-lined box heated with a hairdryer. However, I discovered that this wouldn't work because gallium isn't dense enough to compress the air and push it out of the pump against the outside air pressure. So I tried again using the oil from the vacuum pump, which I believe is rated to not evaporate at 0.1 pascals at room temperature, but I had trouble finding sources online for that, so don't quote me on it. I ended up building this little guy, and although it doesn't show on the footage, I ended up bottoming out the vacuum gauge with it, and managed to make a couple of simple glass discharge tubes with it. It needed a few more tweaks though, so now I'd like to show you what I did, and walk you through how to make one yourself. First, take a 1/4-inch brass NPT plug and drill a hole in it. The size of the hole really isn't that important, just so long as air evacuated from the pump can get through it. I used a 3/32 drill bit. Note that this step isn't strictly necessary as long as you leave the cap loose when the pump is running, and leaving the cap solid will allow you to seal the pump so no oil spills out if you need to move it. When drilling through metal, it's generally better to go slow so that the bit doesn't get too hot and starts wearing down. Large chips or curlicues are a good sign that the bit is sharp and that you're cutting a lot of material. I also like to clean up the chips as I go, so I can see how deep the hole is and don't make a mess. When you get close to the end, try to go slow and not push the drill too hard. Otherwise, you might punch through suddenly and snap the drill bit off. I've lost more than a few drill bits that way. Pump the drill up and down through the hole a few times to clear the burrs from the edges of the hole. And if you want, you can even countersink them to clear the burrs and give the hole a nice bevel. Next, you're going to need to collect your pipe fittings. I'll include links to the various parts I used for this project in the description, but feel free to use anything that fits your project unless I say otherwise. You're going to need the 1/4" brass plug, a 1/4" brass T-fitting, a 1/4" by 1/8" barb fitting, a 1/4" by 4" long nipple, and a 1/4" brass needle valve. This valve is going to be important for controlling how fast the oil flows from the reservoir into the pump. Without it, the oil will get sucked into the pump faster the lower the air pressure inside it became. I tried using a ball valve for the prototype, and it sort of worked, but didn't give me the amount of control I needed over the oil flow rate. Make sure that the arrow is pointing in the direction that the oil will need to flow. This will make up the oil reservoir assembly for our pump. Next, you're going to need a 1/4" NPT vacuum gauge, a second 1/4" T-fitting, a small 1/4" nipple, a second valve, a second 1/4" by 1/8" barb fitting, a 6" long nipple, a 1/4" elbow fitting, a 3" long nipple, a second small 1/4" nipple, a third 1/4" T-fitting, and a third 1/4" by 1/8" barb fitting. You don't technically need the vacuum gauge, and could put a plug or elbow here instead, but I find it helpful for seeing how far along the pump is and whether or not there are any leaks, as we'll see later. You can see here that I'm using a ball valve, but I would recommend that you use a second 1/4" needle valve instead, for reasons you'll see later. Just make sure that the arrow on it is pointing in towards the vacuum gauge, since that's the direction air will be flowing. I like to press the fittings against the work table when putting them together, so that everything is aligned nicely, which will be useful when we install it on the backboard. Don't worry about them being too loose, since we'll be taking care of that later. Now, when I was building the prototype, I was worried about the oil flooding backwards into this part of the pump if the reservoir valve were left open, which is why I used such long pipe fittings for this project. I figured that if the gauge and second valve were up higher than the top of the reservoir, the oil would never be able to flow back up into it under gravity. In reality, most of the oil will end up settling at the bottom here, so your nipples don't need to be as long as mine. Just so long as the one on the bottom is long enough that you have clearance to screw on the reservoir. Oil can still get sucked into your vacuum tubes though, if the pump is already evacuated and the reservoir valve suddenly opens, which is another good reason to have a second valve here. This will be the main assembly for our vacuum pump. Next, we're going to need a capillary tube to drip our oil down into the outlet of the pump, catching residual air molecules in the gap as it goes. I found these little glass medicine droppers were just about perfect, except for one thing. As you can see, they're just a little bit too long to fit into our pipe manifold, so we're going to have to shorten it. Note about where the edge of the pipe fittings reaches the side of the medicine dropper, and make a mark about a 1/4 inch further down. This will create an air gap for the oil to drip through. Then take a glass cutter tool and carefully score the tube at that mark all the way around. You want to apply just enough pressure that the tool actually cuts into the glass and leaves a mark, but not so hard that you shatter the tube. Try to keep the cut straight as you rotate the tool, but if the ends don't quite match up, that'll be alright. When breaking the glass tube along the scoring line like this, What you'll want to do is place both thumbs at the scoring line and try to pull the tube apart at both ends, while simultaneously applying pressure at the thumbs. As you can see, the cut isn't perfectly straight, but we'll be fixing that shortly. Now, for some reason, my landlord doesn't want me using a blowtorch in my apartment, so I had to get permission from my boss to do the next few steps at work. Just try to do this somewhere where you won't catch yourself or anything else on fire, and always keep an extinguisher handy. For safety, I like to keep the torch between my two hands when working glass like this, but pretend that there's an imaginary wall between them where the blowtorch is. As long as my hands never cross that line, they won't get caught in the flame. One time was more than enough. Turn on your blowtorch and light it with a striker. Then put the cut end near the blue tip of the flame and roll it around until it starts to glow red or yellow hot, depending on what you're trying to do with it. This causes the sharp edges of the glass to melt and become smooth in a process called flame polishing. Note that the glass is such a poor conductor of heat that I can hold even a short piece of glass like this very close to the flame with my bare hand and not get burnt, as long as the glass doesn't spend too much time in the flame. Next, we need to flare the end of the glass tube so it won't fall down the end of the pipe fittings. To do that, I like to use this old countersink. Get the end of the glass tube glowing hot again, then quickly remove it from the flame and gently push the countersink into the tube while it's still hot, rotating the tube as you go. This presses the glass outwards while it's hot, and you'll notice that it has a consistency in this state a little bit like heated hard candy or caramel, if you're into that sort of thing. Sorry, the picture's out of focus, my camera needs glasses. At this point, the flare is conical, like the countersink, but if we heat it again and rub it against this graphite block, we can make it flat and pretty close to perpendicular with the rest of the medicine dropper. You can probably get away with using something else instead of graphite, like a burnt piece of wood or charcoal, but if you're going to be working glass regularly, I can't recommend one enough for how handy it is. Once the medicine dropper has cooled, take a tube of silicone caulking and line the flared end of the dropper with it. This is the only time I'm going to recommend you use silicone for any part of this project, because silicone isn't perfectly airtight, as we'll see later. However, silicone is the only easy-to-get sealant I could think of that will also be able to handle the high temperatures of upcoming steps. I used Faraday wax in the prototype. Next, press the caulked medicine dropper into the open end of the main pump assembly and wipe away the excess silicone. Try to make sure that it doesn't get into the threads of the pipe fittings. Next, find a nail, paper clip, or a straight piece of wire of appropriate size and poke it through the end of the medicine dropper and out the other side of the barb fitting so that the dropper will set in line with the hole in the barb fitting. This will ensure that the oil droplets fall straight down into the hole, catching air as they go, rather than dribbling down the sides of the fitting. Leave the silicone to set overnight, and then remove the wire. Looks pretty straight to me. Next, we're going to seal up the pipe fittings by soldering them together, and for this, we need to take everything apart again, because someone got a little too excited and forgot to add the flux. Flux removes the oxide layer from the outside of the pipes so that the solder will stick to and alloy with it. And I think that as the flux evaporates, it also creates a slight vacuum that helps suck solder into the cracks in the threads, but I'm not sure about that one. Take an acid brush and brush some flux paste on the end of it. Then paint the flux onto the threads of your pipe fittings. As you can see, I should have trimmed the brush hairs a little shorter, as that gives you a little more control over how much flux you apply and where you spread it. You only need a thin coating of flux on your pipes, but I applied way too much of it, and we'll see in a little bit why that can be a problem. Make sure you paint flux onto both the male and female threads of your pipe fittings. Again, shorter brush hairs would come in handy here. I recommend using a water-soluble flux because it makes cleaning easier later. Apply flux to all of the pipe fittings and screw them back together. Get them as tight as you can, but don't worry about getting them too tight, as the solder will fill in the cracks wherever the pipes are loose. You can press the fittings against the table to make sure that all the fittings sit straight. Do this for both the main pipe assembly and the reservoir pipe assembly. But don't apply flux to the plug at the top of the reservoir, as we'll want to be able to screw this on and off later. Now we're finally ready to solder. Extend your soldering wire and bend a hook in the end of it, so it'll be easier to apply exactly where you want it. Then, light your blowtorch and hold the pipe assembly with a pair of pliers to keep from burning yourself. Apply heat to the pipes until they become hot enough to melt the solder upon contact. This should take a minute or two as the entire assembly heats up, so you don't need to press the solder to the pipes as hard or constantly as I did. Also helps if you don't have a fan running in the background blowing out your blowtorch. Try to apply solder at the top of the fitting and with the female fitting downhill from the male, so that gravity pulls the molten solder down and around to the bottom, following the seam between the two fittings and filling it in. Check all around the seam to make sure that the solder has filled it in completely and that there are no gaps where air might get in. The smoke you see coming out of the pipe assembly is the rosin burning off. That's normal, but again, I used way too much of it, leaving a layer of char on the inside and outside of the pipes, which I was worried would contaminate the oil or the vacuum later. Do this for all of the seams between the pipe fittings. Extend the soldering wire when it starts to get short, and reposition the pliers when you need to hold the pipe assembly at the other end. Remember to take the pipes out of the flame before applying the solder, otherwise the solder will melt and fall off, getting wasted. Like that. Let's see how long it takes me to figure that out. Can you tell this is my first time? At this point, I would like to bring to your attention that the ball valve has nylon gaskets around the ball that allow it to maintain a seal while turning. However, they'll start to melt when heat is applied for soldering. This is why I recommended that you use another needle valve here instead of a ball valve like I did. The handle's also flammable. You'll also want to keep a careful eye on where you have the flame pointing at this stage, as the heat can easily melt the plexiglass cover with the vacuum gauge if you're not careful. Now he's finally starting to get it. Set the pipe assemblies aside and when they're cool, twist them together and apply solder to the final seam. Cross fingers that I sealed everything up all right. Back at the lab, I used some 90% isopropyl alcohol to try and wash out the worst of the flux residue, wiping down the outside of this little steampunk art piece with a paper towel, before opening the valves and pouring some inside, sealing the outlets and sloshing it around. Then drain the fluid and leave the pipes to dry out in a fairly warm place for a day. There should not be any water residue in the pipes when you run the pump. I took some time to cut out a new plexiglass cover for the vacuum gauge using a hole saw. Now it's time to build the backboard. I found this 12 by 24 by ½ inch plywood project board to be almost perfect, but you can use any old piece of ½ inch ply for this, as long as it fits the pipe assembly. For this stand, I'm going to cut about 6 inches off the bottom of the project board to make a foot that'll hold the stand up, but feel free to build yours any way you want. Take a tape measure and mark on each side of the board where you want to cut it, using a ruler or carpenter's square to draw a straight line across the board. Just make sure that you leave at least 6 inches or more below the pipe assembly, or the electronics we'll need to install in a little bit. Next, secure your piece of plywood and start cutting along the line. I used a hacksaw because I didn't want to tear up the nice finish on the wood. But it couldn't cut all the way through. Try the jigsaw? Huh, didn't turn out so bad after all. Next, find the store-cut end of the backboard to be used as the foot of your stand, and mark the halfway point on it. This should be 6 inches, but they're never cut perfectly, so measure 6 inches from both sides and find the center of both of those marks. That's the real halfway point. Then, measure the thickness of your plywood, again, not quite ½ inch, and try to mark about half this value on either side of your center line. Next, make a mark above these points, half the width of the footboard you cut off, in my case about 3 inches, and draw a rectangle to define the shape of the slot we'll cut into the backboard to fit the two together. Do this for both boards. I've learned that it's helpful in carpentry to put hash marks on the part of the board that you intend to cut out, so you don't accidentally cut off the wrong part. Secure your boards again, and use the jigsaw to cut out the pattern. Try to cut on the inside of the lines rather than the outside to secure a snug fit, and if it's too tight, you can always trim more material off. You can't put it back on. Sorry about the bad camera angle. Wait a minute, how are we going to cut that sharp corner? The jigsaw's blade has a little bit of give to it, so twist the saw to cut an arc towards the center of the pattern on each side, cutting out a bullet-shaped cavity. Then, use the jigsaw to carefully trim away the material remaining in the corners. Do this for both boards and slide them together to see how they fit. Trim away any more material as necessary. Now for the literal heart of this machine. I bought this little 6-volt peristaltic pump from Adafruit. It pumps fluid through these tubes by running a trio of rotating rollers over them and squeezing the fluid through. This will be perfect for our pump because the motor never even needs to actually touch the oil. Seeing where the tubes will need to reach, pick a good spot on the backboard where the pump can be mounted. If you want to, you can separate the pump from the motor and use it as a stencil to mark where you want to mount the pump. Next, find a hole saw that's just a little bit too small for the motor to fit inside. I believe this one's about 1 1/4 inches. Secure the backboard again and use the hole saw to cut out the hole you stenciled. The drill bit in the middle of the saw makes it much easier to keep the hole centered. But if you don't have one, you can use the same hole saw to cut a guide out of a piece of scrap wood first, and clamp it down over the stencil. It helps if the hole saw is tightly secured into the power drill, and to vacuum up the chips as you go to keep things tight. Once the hole saw starts cutting into the wood, it helps to rock it around in little circles. And when you've cut a little over halfway through the board, flip it over and start cutting from the other side using the center drill hole as a guide. This way, you won't tear up the wood when you finally break through. Next, put the motor in the hole and mark where the holes on the mounting bracket are. Find a drill bit that fits through the holes on the bracket, I think I used a 1/8 inch bit, and drill through the marks you made on the backboard. Again, sorry for the bad camera angle. While we're here, let's mark where we want the on-off switch to go. This isn't strictly necessary, but it sure is convenient. Place the switch against the backboard and do your best to trace out the edges. Then make some marks a little deeper in, matching the width and height of the backside of the switch. This is the area we'll cut out, so that the switch slides into the backboard but catches on the rim. Next, find a drill bit a little smaller than the width of that rectangle, and drill through the middle of it. The bit will tend to drift when you first start drilling, so take it slow and consider making an initial depression in the wood with the tip, a countersink, or a smaller drill bit for it to fall into. It helps to clear the chips away, so you can make sure you're drilling inside the lines. If you cut outside the lines though, you can just shift the entire switch hole a little bit to the side to compensate. It's not a big deal as long as it fits. And again, drill a little more slowly when you start reaching the opposite side, so you don't tear up the wood too much when you punch through. Next, use the jigsaw to trim away the corners around the hole we drilled out, the same way we did for the slots in the stand. Kinda tricky reaching all of them without elbowing the camera again. Now how am I gonna get that last one? Won't hurt to pivot the clamps a little and give myself a little extra room. And now you can see better too. Check to make sure the switch fits. If it doesn't, trim a little bit more of the perimeter away until it does. Now let's install the motor. You'll need 2 440 bolts, matching nuts, and 4 washers of similar size. Thread the bolts through 1 washer each, and then through the bracket and holes in the backboard. Then do the same for the nuts and remaining washers on the opposite side. These 3/4 inch long bolts were just barely long enough to catch the nuts, which makes them fiddly to try to put together with my fat fingers. But they were the only ones I could find at my nearest hardware store, so if you can find some that are longer, I'd strongly recommend it. Use a wrench and screwdriver to tighten them down. Next we need to add our power supply. The motor is rated for 6 volts, 500 milliamps, so I found an AC to DC wall plug on eBay with a matching voltage and cut and stripped the wires on the opposite end. Now, while the positive and negative terminals on the motor are already marked, it'll drive the pump backwards compared to what we want, so we'll need to hook up the terminals in reverse,
red to black, and vice versa. If you aren't sure, you can just plug in and tap the terminals in each configuration and see which way the pump flows. And if you get it wrong, you can always swap the hoses later, so it's no big deal. Take a hot soldering iron and press the wires to the terminals. It helps if there's already a little bit of solder on them. And like the pipes, we're trying to get the terminals and wire hot rather than the solder itself, so the solder will wick into them and stick them together when it solidifies. To complete the circuit, we'll need to connect one of the switch terminals to the motor and the other to the power supply. Find an extra piece of wire, cut it just a little bit longer than you need it to be, and strip the ends. Like I said, it makes things easier if there's already a little bit of solder on the wires, so get some electronic solder and your soldering iron, and paint a little bit of the solder onto the ends of the wire. The more surface area, the better, so flatten out the ends of your wire beforehand. This will make the wire hot, so be careful when picking it up when you're all done. Do the same thing to the terminals on the switch, and then solder them together. The motor to one of the switch terminals, and the remaining switch terminal to the remaining wire on your power supply. It doesn't really matter which, but it helps to avoid short circuits if you don't cross your wires. If you're worried about the electrodes being exposed like this, you can coat them in hot glue when you're done to insulate them, and staple the power cable to the side of the stand to keep the connection from getting ripped out if you try to move it. Now all we have to do is plug it in and give it a test. You can kind of see the residual oil from testing trying to flow out of the tube on the left, which is exactly where we want it to go. Now it's time to bring everything together. Place your pipe manifold where you want it on the backboard. Then get 3 half-inch copper pipe straps and place them where you would like them on the manifold for support. They don't have to be copper. You can use something cheaper if you want, but I wanted it to look nice for the camera. Mark the holes in the straps on your backboard and use some screws to hold them down. I had these little wood screws lying around, and what you're going to want to do is find a drill bit that's about as wide as the center of the screws, but not wider than the threads. I think this one is about 7/64 or 1/8 inch wide. Once you recaptured the runaway drill bit, drill some pilot holes for the screws where you made the marks from the straps. Replace the pipe assembly and straps and screw them down. These particular screws have given me trouble in the past, stripping out easily, so I would recommend tightening them with a screwdriver instead of a power drill. They don't need to be more than hand tight anyway, since the idea here is to make the whole assembly easy to remove if you need to troubleshoot it, as we'll soon see. Now we're ready to hook up the pump. Take the inlet hose and attach it to the barb fitting on the bottom of the pipe assembly. For convenience, you can cut the hose to length so it's not flopping around or letting air leak in, as we'll see later. But make sure that there's a little slack in it so you can take the pipe assembly off the backboard and move it around if you need to. Do the same thing with the outlet hose and attach it to the barb fitting near the top of the reservoir. It would also be a good idea to make sure you know which hose is which before you cut them. But like I said, you can swap them later if you need to, since they're connected to the pump with little plastic barbs of their own. It can just get a little messy is all. Slide the foot into the bottom of the stand, and we're ready to give this thing a test. Remove the plug at the top of the reservoir, and carefully pour in a little bit of vacuum oil. It's worth acknowledging at this point that you can't use cooking oil, motor oil, or any other oil instead, because this particular kind of oil has been engineered to not evaporate at low pressures. It's also worth mentioning that you can't use traditional mercury in this device either, because mercury will dissolve any other metal except steel, which is why they won't let you ship it on airplanes. Fill until it just reaches the branch and the T-fitting. You don't need a lot of it. Then screw the cap back on to minimize any risk of spilling. Like I said at the beginning, you can skip the hole and just leave it loose when it's running so the air has somewhere to escape. Now for the moment of truth. Turn on the pump and just crack the needle valve until you see just a few droplets of oil flowing through the pump hose. As few as possible without being completely absent. If the oil flows out of the reservoir too fast, the reservoir could empty out completely and break the vacuum. You'll need to tighten the valve as the pressure drops, which doesn't seem to be going below minus 0.2 bar. That means we probably have a leak somewhere. Nope, it's not the ball valve, which was my first guess. Looks like we'll have to do some troubleshooting. Good thing we made it easy to take apart. Give me a minute. Alright, I'm back. And I found out a few things you might find useful for your own troubleshooting. Firstly, hot glue is pretty ideal for finding leaks. While it's melted, it gets pulled into the cracks and seals them up, but it doesn't end up sticking to the metal, so it's easy to take off later compared to something like silicone caulking. I just applied it to all the joints. I was worried that there was a leak somewhere in the soldering, but it turns out they were all perfect. The leak was actually coming from the needle valve. There's a little nut that the shaft runs through that controls how tight the knob is to turn. I'm guessing that a little air was leaking in through there. So if I tighten it with a wrench, let's see if that makes things better. Let's close the ball valve, and oh yeah, that's how fast it's supposed to be going down. I know it's a little bit hard to see against this light background, but let me try to show you. As I adjust the needle valve, oil starts dripping through, only a little at first, flowing around the edges under surface tension, but eventually forming droplets that completely block the— oop, that's too much. Let me dial it back. I know the oil is flowing a bit fast to see, so if I pinch the hose, you can kind of get a better idea of how interspersed the oil and air bubbles are. Again, that's too much oil. We only want a little bit. Yeah, that's better. Only a few at a time. And you can see now that there are small foamy air bubbles forming on the inside of the tube. That's air leaking in through the silicone itself, which is why it's generally unsuitable for vacuum applications. This pump seems to be able to keep up with it, but latex or neoprene hoses would be a little more airtight. I just wanted you to be able to see it, and the transparency of the silicone makes it easier to judge the oil flow rate. You can also see, as the pressure gets lower, that the oil comes out of the pump slower and in vibrating pulses. This is because the air outside the pump is pushing the oil in harder than the residual air in the pump can push it out, so the pump has to make up the difference. Let's see how long it takes to evacuate. By my reckoning, about 3 minutes to completely bottom out the gauge, which I think is pretty impressive for a $25 pump that wasn't designed for this at all. Now let's turn it off and see if it's just keeping up with any leaks. The gauge isn't going back down, which is a good sign that there are no major leaks. But let's give it a little time and see how fast the air gets back into it.
1 hour later.
Well, it looks like it may have gone down by maybe half an inch of mercury, but it's hard to tell.
2 hours later.
Okay, it's definitely gone down now by about 0.04 bar, but it's still taking so long that I think it's just leaking in through the silicone tubing.
3 hours later.
It went down another 0.04 bar. As the pressure inside the pump increases, I would expect air to leak in at an exponentially slower rate.
5 hours later.
Down to 0.12 bar, so it definitely seems to be slowing down a little.
Early the next morning.
Down to 0.3 bar, so it's definitely not linear.
Later that same evening.
Okay, it's taken almost a day and a half for this thing to get down to half pressure, so I think I can confidently say that there are no major leaks.
Overall, I'm really pleased with this little vacuum pump. It's small, it's quiet, it won't break the bank, and it can be made by almost anyone using parts you can get at your local hardware store. Now, obviously, it's not going to work well for high volume applications where you have a big vacuum chamber that you need to evacuate. But for little vacuum tubes like the ones I'm trying to make, it's just about perfect. If you want to scale this up and don't need the pressure so low, maybe use bigger pipe fittings or a bigger pump, you could probably do that minus the dripper, and it would basically function like a piston pump, just using oil as a sort of continuous piston. It kind of does that already when I don't have the dripper running. And if you don't want to solder the joints together, that's okay too, if you don't need the pressure at an absolute minimum. Like I said, the prototype worked almost this well, and I sealed it up with Teflon tape and silicone, so you don't need to play with fire to build it if you don't want to. Just know that oil will slowly leak out around the bottom of the reservoir no matter how well you seal it. All that said, however, just how good a vacuum am I actually getting? The oil is supposedly rated for about 0.1 pascals, but my vacuum gauge isn't that sensitive, having a maximum sensitivity of maybe 1 kilopascal if you squint. High sensitivity digital vacuum gauges are also expensive, so in the next video, I'd like to try making one of those too, and share with you what I learned from the process. If you'd like to see how that turns out, be sure to press the subscribe and bell buttons under the video to get notified as soon as the next one's ready. And if you like this and want to see more, consider pressing the like button too. I'm not doing YouTube for money, but it helps this video find more people like you who will enjoy it. That said, thanks again for listening, and I hope to see you here again in the next video.